Today I'm going to talk about a little project I've been working on for the last while. It's a technique for automatically characterizing a system with nothing but some raw data from the system. So let's say we have some system that to us right now is just a black box. We put a known input into it and we measure an output, like so. You may even recognize this simple example as being a first-order linear equation. In a nutshell, because the output from the system is a linear summation of separate terms, and because these days computers are very fast at performing a lot of computations quickly, we can effectively do guess and check in reverse to find what the governing equation of the system is. If we look at an even simpler system, we can see that the equation that has these initial conditions, and in this case y equals sine of x, as a solution, the governing equation of this system can be broken down into some linear combination of all these coefficients raised to some exponent. Because we have recorded data of the input, which is the function r, and output of the system, which is the function y, we can use that output data to approximate derivatives of the output, and we can generate these terms up to a finite order and just sum them together and see if they equal 0. Obviously, there are a lot of possible combinations to try. In a simple second-order linear system like this, there are literally billions. But there's a simple trick we can employ to reduce that number drastically. We formulate a vector out of all the exponents of each coefficient in each term. We define a finite value for the exponent of each coefficient of this vector. Because we can't try literally everything, we have to be a bit careful and try to estimate what order the equation probably is and what types of terms might appear in it. That gives us the red vector, which corresponds to the maximum exponent of each coefficient in each term that we would like to test. Then we reorder this vector from smallest to largest and keep track of what operations we did in doing so as a matrix such that we can undo this ordering and get back our initial assumed general form of the system's governing equation later. Now what we can do is treat each element of this vector as just a digit in a number that has the base plus 1 of whatever the largest element in the vector is. In this example, because we are considering the second derivative of y raised to the third power as being a possible coefficient in one of our terms, that means that this reordered vector is just some number in base 4 with 21 digits. But because we reordered the exponents from smallest to largest, we don't actually have to count that high. We only count up to whatever number at the bottom left turns out to be in base 10. And the beauty of this strategy is that we have reduced trying all these other different combinations of the derivatives of our system's output to just counting in base 4 and solving a few matrices. If we take the vector representing the powers of the combinations of coefficients that we know is the equation we're looking for in this simple example, and if we numerically evaluate it, then we end up with the sum of terms with unknown coefficients. And in order to finish checking if this vector corresponds to an actual governing equation of the system we're investigating, we need to find what these coefficients are. The next trick that we use in this method is the fact that if y and its derivatives are just some vectors representing a function's values throughout time, it has to numerically solve this governing equation for the entire domain of time that we are considering, because that's how differential equations work. So we can use this fact to create as many linearly independent equations as we need in order to solve for these constant coefficients by just sampling our raw data and its approximated derivatives at different points in time. We have to be a bit careful about how we sample, though. We want to create a system of equations that does, in fact, have a single solution for our constant coefficients. And because the matrix that we end up solving, depending on your sample data, can end up with small entries, there's a good idea to normalize the computed coefficients like this, because otherwise, if the matrix is singular or near singular, they can end up being very large values, and this strategy gets rid of that. Once the constant coefficients have been computed, you have to be careful about how you test to see if the resulting summation of the terms equals 0. If you approximate higher order derivatives from the measured output of the system, you will need to shift the raw data depending on how you centered the derivative. This is an example of a forward difference of second order. The second order derivative is centered on the raw data index plus 2. So for things to sum to 0, you need to match the second order derivative with the raw data at the correct index, or it may not be closer to 0 than whatever tolerance you find acceptable. Where here I have my tolerance equal to delta x. Furthermore, because once again this equation should be true for all x, I sum these terms over the entire domain of recorded data as a way of establishing greater significance of different solutions. As we will soon see, because this is a numerical technique, it isn't foolproof, it can go wrong in surprising and unexpected ways. So here we have a simple test. I'm basically using y equals sine of the square root of 2 multiplied by x as a recorded output to try to find the corresponding linear ordinary differential equation that solves. And with this guess mask, I've limited the maximum powers of the coefficients to be close to what they're supposed to be. There are still tens of thousands of possibilities within this bound, but as you can see, the script executes in a fraction of a second, and via the highlighted correct guess number on the right, we can see it found 383 governing equations within these bounds that y equals sine of the square root of 2 multiplied by x solves. If you think that 383 governing equations seems high, you are correct, because the way I have set up the implementation of this algorithm within the script, it finds a whole lot of trivial solutions like what I have highlighted here. The second order derivative of y minus the second order derivative of y is of course 0. The way I have this algorithm currently implemented in this script has not been optimized for speed or anything really. As an example, a second order system of 3 terms raised to a maximum power of 2 across all digits takes about 2.5 hours for my laptop to power through. But there's a lot of low-hanging fruit regarding optimization, considering that all we're doing is counting and multiplying matrices. We could make this type of computation go much faster by either running it on a GPU or multi-threading it. You can eliminate trivial solutions during the initial computation. There are some ways of doing so, but for now I simply apply a second script to the computed governing equations to eliminate the trivial ones. Doing that cuts down the computed governing equations to about a third of what they were, which still seems large. Also, these equations may seem odd, like they couldn't be real governing equations, but if we algebraically substitute our system output data into these terms, we can see that the sum of these two terms actually does equal 0. We can make another script to algebraically check all computed equations, and in this example, all 139 of these equations actually work. And this is one of the nice things of this kind of otherwise cumbersome numerical method, is that we can discover surprising things about the system in question. Because as long as we define our metric for testing for 0 carefully, we will find all possible governing equations within the boundaries that we define. Now we can go on to demonstrating something even more interesting, and that is that this methodology has general utility via rediscovering the logistic equation, which is a well-known one-dimensional nonlinear differential equation used to approximate population growth. The logistic equation has a known solution, which is what I use as simulated data from a black box, and I've let the powers, the different coefficients, range a little bit above what they're supposed to be, but not too much. And here is where we encounter another issue with this method. We found 259 governing equations, and this is one of them. It doesn't seem like it should be legitimate that the first order derivative of y squared plus y multiplied by this tiny number equals 0. But numerically at least, this actually does pass the metric I defined for testing the sum of these two terms being equal to 0 across the x-domain. This actually does make sense if you think about it. Y is some exponential function, and the derivatives of exponential functions are multiples of the original exponential function. So when we solve for the constant coefficients that make these two terms sum to 0, if we don't apply any constraints on what value those coefficients can have, we are basically guaranteed to find governing equations like this one, where two seemingly unrelated terms sum to 0 if we multiply one of them by some odd, either very large or very small number. And some functions will always do this. But I discovered an easy way to fix this, though I do not have a very good rigorous argument as to why it works. It just does. And that is to just eliminate governing equations that have coefficients whose absolute values are smaller than the step size of our data. And this does make sense in a simple way. We're basically just saying we can't have resolutions smaller than a square whose side length is our step size. Another thing to note is that because this is a numerical method, these coefficients aren't exact. We are effectively solving for an approximation of the coefficients, as in this example, these values should be exactly 1/2. Also, the r coefficient's powers seem like they're wrong, but the r coefficient in our assumed general form is the forcing function, and because there is no input to the logistic equation, r in this case is always just a value 1 raised to some power. This is another limitation of my current implementation of this strategy as opposed to the strategy itself, that while these are technically correct, they are redundant equations. So we can use this strategy to, after possibly a very long computation time, find the governing equation of a system that could otherwise be a black box. So what? What is this good for? Well, the governing equation by itself can tell us useful things about how to manipulate and control a system's behavior. Let's take the logistic equation as an example. It approximately describes population growth. R is a parameter that describes the exponential rate of population growth. Y0 is the initial population, and everything here has been normalized with respect to the environment's maximum carrying capacity for the population in question. We can see that a population will exponentially approach the maximum population that can be supported by the environment that the population finds itself in. The main thing that a governing equation is useful for in describing a system's behavior is that it can be used to find the fixed points of the system and classify them as either being stable or unstable. You find the fixed points by solving for where the derivative of the dependent variable in question equals 0. Then you just find the sign of that derivative within the neighborhood of those fixed points, and this will tell you how that dependent variable changes within the neighborhood of that fixed point, whether it will attract towards the point, making it stable, or repel away from it, making it unstable. In the case of population dynamics, if the population Y is below the environment's carrying capacity, the population increases towards the carrying capacity. If the population is above the carrying capacity, it decreases towards the carrying capacity. Well, this is a very simple example of a nonlinear system that isn't even a very good approximation of all the aspects of population dynamics. Nonlinear systems become even more interesting and more broadly relevant when they are multidimensional. In the future, I'd like to generalize this same strategy to multidimensional and vector-based systems. The computation time will probably increase exponentially, but as I previously said, there are a lot of very simple strategies that can be employed to make such a computation go a lot faster. Even a couple of decades ago, a personal laptop would have struggled to do the examples I've shown today, which ran in a fraction of a second. That's all for now. Thank you for watching.